Just let me know when we can start. We can start. Yes. Okay. So thanks for the invitation. I'm happy to be here, and I guess you would also like to have an interaction after the talk. So I'm having a very brief overview of what we do in our group. Um, and when I say vignettes, I just mean it's a brief characterization. Okay, just a fancy word, but it just means a brief characterization of computational physics and statistical computing with personal touch. That's what it means. Vignette. So I am Murugesan. Don't know me, and our group is Computation and Statistical Physics group at the Department of Computation and Data Sciences. It's right next door for people who have not been there. Actually, the name of the group is kind of mismatched to what we do. We really don't do statistical physics. Okay, so for those people who are expecting statistical physics, Including, and there are two problems, for example, that I'm going to talk about: integration ID, randomized algebra. I'll just give you some examples today. And then the traditional area of numerical algebra and matrix analysis, something we have looked at. I'll just give you a few, one or two examples there. And the same thing with scientific conclusions, the specific applications, again, two examples, at least principles used in solving the problem so that you can really see what's working. And then some of my collaborators students work in simulation of optical problem. We do the simulation, but the collaborators in physical chemistry and nanoscience may actually make those materials, test them, and we do those kind of practical material development as well sometimes. And then my MTech core students work on statistical model data analysis, a more wider contemporary topics of more public interest, like COVID-19. Recently, this year, we studied university rankings. Obviously, is known answer. The rankings don't mean anything. But anyway, so it's just to show people. Sometimes you have to throw something that is an opinion, but then you have to rigorously show. But anyway, so first topic is statistical computing. And we specifically look at sampling and estimation in ID. That's our interest. And ID meaning we are looking at vectors, ordered set of numbers, x1, x2, xn. And n could be large here. Okay? So we are looking at that kind of space. And one of the problems that we were interested in this area is integration. So if you do numerical integration, you would not have, yet a second year students would have done that class. I'm thinking some of you at least. The way you would integrate a function numerically between domain A to B, one dimensional integration, you would take points in between A and B, evaluate the function, fit a polynomial because polynomials are easy to integrate, and then integrate. Integration of a polynomial is any method that you come up with integration implicitly does this. Okay, it only fits a polynomial and has a formula for the integral of it. Any method. There's so many other methods that are there to work, but the principle is this. Okay. So the issue with that is 1D you would require, let's say, C points. 2D you would require C squared. Okay, for example, if you wanted to integrate the x1, x2, you have a function, two variables x1 and x2. The function is defined in the domain, x1 is the x-axis, and let's say x2 is the y-axis, and you have a cube. The function is defined here, then you have to discretize this domain. So the number of points becomes C1 instead of C squared. Okay, so you have to discretize this cube. Instead of a line, you have a cube now. That is like area. Sorry, square. So 2 cube. You can call it a 2 cube. So then we go to a 3 cube for 3 dimension and 4 cube for a 4 dimension and so forth. So in an n cube in n dimensions. Okay. So you will have n such variables. There's a typo here, and then you have to discretize the domain, and so naturally the computing cost goes up exponentially. Okay, numerical methods. The good thing with numerical methods is they give convergence guarantees, all these things, but and they work for almost all functions, all domains, but then the effort goes exponentially. It's not realistic to use numerical methods when n crosses 10. Okay, and these are called NP-hard problems because you cannot give guarantees that you can solve the problem in a polynomial term where n is the variable here. So the other approach is to do statistical integration, which is you don't discretize the grid explicitly, just sample the domain randomly. Okay, this could be, for example, this cube is straightforward, generate random coordinate cardinal directions. Points in the cardinal direction x1, x2 using some random number generators for x1 and x2, and then go to the point, sample the function, average, and then find the average of the function into the domain area will give you the volume, which is the integral. So that is a rough way of doing it. But the devil in the details is finding the volume. Cube is okay. of any other body is not trivial. Okay, in ID. So that's the given detail. But anyway, so this simple method is called Monte Carlo sampling, which you would have heard about. There is another one called quasi Monte Carlo, which is you generate the points not using random numbers, but using some formulae. Then there is MCMC, which is Markov chain Monte Carlo, where actually you randomly walk in the domain. The samples are not independent anymore because they're correlated with walking. But then there are other advantages because you can sample non-cubic domains, other shapes. You can sample in any required, you know, density, probability density, not just uniform. So there are other advantages. You give up something, but you are correlated, your samples are not independent, but then you get other advantage. Domain could be more complex. The sampling could be in other based on other densities, not uniform. So that is one approach. And then still that has some difficulties. We can work on in convex domains, not in any other domain. And then if you wanted to do the same thing in arbitrary, non-convex, really rough boundary, then there are challenges. And we have proposed some methods like n-square multiplier. That's something we work on. And this method is just line integrals. You shoot line integrals randomly in all directions, average them moment. There's some real ideas there. It's not quite straightforward, but that's something we have proposed working on, comparing them with the prediction methods and so forth. The other work in the statistical computing, and remember, if I have to go back, the goal here is not to get very accurate answers. Okay. Remember, numerical method might take 2 days for a 100D problem. The question is whether in 2 days your statistical method gives better answers. Okay, that is the goal here. So you cannot, expect the same, sixth decimal, seventh decimal of precision that you were used to in a numerical method in a small problem. Larger problems you can't in statistical methods. You're looking at 5% relative error, 4%. That order of accuracy. Okay. And that is true in any randomized method. So that's why I just went back and had to tell you that, because let's take for example numerical linear algebra, which is about problems like this where you have to multiply two matrices, solve for x in Ax equal to b. A is a matrix, b is a vector, given vector, and x is the unknown vector. Solve for you would have factorization problems, factorize a into two factors, lower triangular, and decompositions, and so forth. So all these are done very efficiently with numerical algebra algorithms. Okay, and these algorithms scale as roughly n squared or n cubed, depending on whether they're sparse or dense. Dense matrices n cubed, sparse n squared, and depending on what you're doing. For example, the different linear solve you could do in n squared. I'll come to that in the next slide. So roughly n squared n cubed. Okay, that's the ballpark number that you're looking at. And if you typically look at what we are doing currently, we are looking at matrices dimensions 10 to 100,000 workstations, about 1,000 to 10 million or 100 million in a HPC high performance system. So you can imagine that 10 raised to 5 means n squared. N is 10 raised to 5, that means n squared. Elements or n squared computing means 10 raised to 10. That is roughly a minute to, so in terms of minutes, if you were solving a, working on a matrix of around 100,000, maybe even an hour. Okay, that's the ballpark. You cannot do more than that. It's not reasonable to be doing on a workstation. There are applications where this is not good enough. You might want an answer not in an hour for a 100,000 problem, but in a minute, and you are ready to compromise on the errors. Remember, numerical methods, linear algebra, including give you those algorithms are very accurate. Like say 10 raised to minus 6 relative, or 1 part in a million. You may not require that much of precision. So what you do, you take numerical linear algebra and then impose statistical sampling on those methods. Okay. Those kind of methods, they trade off accuracy for speed. Again, you might be looking at 1% error instead of 1 and one part in 100 error, relative error, then one part in a million. And then you would be able to speed up things. And for example, the storage also becomes smaller. You would be dealing with things which are on the fly, streaming, and you don't want to store things and those kind of applications. And so far, there has been some success in two things. For example, finding the first case singular values in vectors of a matrix. Singular values is something we have to deal with. And there's something called CUR decomposition, which basically means C is the sampled columns of A and R are the sampled columns of row. Sometimes you'll get data matrices which are not, the rows and columns mean very different things. Biology, disease, phenotype, gene, something. So you might want to not do any other decomposition like this. They'll mix up row and columns. Okay. So you would want to keep the row as it is, column as it is. Give it a representation which is slightly tricky. So you have an in-between matrix U. So CUR. Okay. So that is the rough motivation. So basically, these two first singular values, CUR decomposition, are the examples of successful randomized methods superimposed from numerical. That's something we do. The other example I do is go back to traditional algebra. Again, if you wanted to solve Ax equal to B, like I said, you're solving a problem which is 10 more than dimensions are 10 raised to 3, 4, and so forth. Like I said, that might go to an R. You won't want to, if it is n cube. So what you could do is, you could solve this problem iteratively. That is, A is given, B is given. You start with the random guess 0, and then iteratively improve to x1, x2, etc., all the way approaching the right answer x. Okay, it's an iterative way of solving. That, it turns out, can be solved in n squared instead of n cubed. Okay. Here, the what you are losing is you don't get an explicit A inverse. For example, if you did by hand, you would have found A inverse x equal to A inverse B is what you would have done. Okay, that means you get explicitly A inverse, and you could use the A inverse again for another B. Now that advantage is lost, but in return, what you gain is you solve in n squared operations, not in n cube. So what is, can R could be done in 2 minutes. So there are some advantages if you're not using the A inverse again. And so these kind of problems typically depend on the residue. That is, each time you see what is B minus AXK, the residue, the difference between right and left side of the equations. But the issue here is residue is the only thing known, and that doesn't tell you exactly what the error is. The error is x minus xk. No, x is the actual solution, and there's a difference of A here. You can see that. So that means you really don't know what the error is. You only know what the residue is, and that can be, the difference can be really bad if this, depending on the properties of this A matrix. And I'll give you an example here. For example, you are running some solid solution Ax equal to B for x, and this black line is the actual error. This color, like green, is the residue. Okay, and this pink line is the estimator we proposed, and you can see the black line and the residue are very different. Black is the actual error, residue is green. So what we do is we try to estimate it. Initially, the estimator doesn't work because the problem is not converging. Once the error starts falling even a little, then the estimator starts working, and you can see there's not much between the actual error. The residue is still orders of magnitude larger. So you won't know when to stop. So only if you know the error, you can stop. No, residue doesn't tell you when to stop. Of course, xk, is it good enough? K type ratio. That's the problem. And then the other problems you can imagine are, eigenvalue problems. And we specifically worked on matrix analysis. For matrices with that periodicity in the entries. That means some of the entries of the matrix are repeating themselves again and again. Okay, you don't have new entries, the same entries repeat. And one of the properties for not all such matrices, but some of them, is that initially when the matrix is small, remember it contains all the entries, the eigenvalues can be anywhere. This box is just imaginary and real axis, anywhere, any complex number. Then as the matrix size increases with the same entries, of course repeated entries, the eigenvalues all converge to certain curves in the complex plane. Okay, So as the matrix size increases, you can predict the eigenvalues more accurately. It's counterintuitive. You would think the larger the matrix, harder is to find the eigenvalue. That is the numerical methods. This is a counterintuitive way of finding the eigenvalues. And so this approach works for right diagonal matrices with periodicity and other. And you could take right diagonal matrices to tensor products, and so you have eigenvalues of other matrices. I won't go into the details, but it gives you a tool to find eigenvalues semi-analytically instead of the numerical. So if you provided if you know if you have a formula to find these curves, okay, that is the tricky hard business. And then of course that is leading to exams. Okay. And the other area thing we've done in matrix analysis, always in matrices you're looking for decompositions. Okay, and the motivation is if you have a decomposition of a matrix into components, each of this component is simple, okay, to operate on computing perspective or an analytical perspective. It helps, makes it life easier. Correct? No? And more so if some of these terms can be ignored. Right? So the two things you would want the decomposition, each entry in the decomposition to be simple, and then you would want such a decomposition that most of the information is in the first few terms, so that you can ignore the other terms. That is also very helpful. So the other thing we have done is propose this circulant decomposition of the matrix, where R is a circulant matrix, which means the entries on the first row repeat themselves all through the matrix, just one shift in the row and column number. Okay, that's a circular matrix. And B is just a diagonal matrix with all entries periodically on the units. So this decomposition, it turns out, helps all matrices with periodicity. So that's something. Here again, here we lose accuracy. Okay, so this method is double advantage. It gave you more accuracy, more speed as n increased. That is rarely happens. So this is the more usual situation where you trade off accuracy for speed. So to reduce dense matrices from order 10 to n square using this decomposition for matrices with some periodicity on the diagram. So this is another example. The other example that I'll give is again why this is classic numerical methods kind of a problem. So, for example, if you wanted to integrate a function, let's call this simple integral f of x dx, and f could be a complex value function. X could be real, but f of x could be complex. And so you wanted to integrate along x from minus infinity, and this f is a complex and a nasty guy with some infinities on the real axis. It could have what you call poles, then its phase could be indeterminate, it's a complex number, remember. So it could be a integrate. In those situations, what you would do is, you try to integrate it, do a contour integration in the complex plane, and you just to avoid this bad points. You have dark lines telling you where the bad regions are, which you do not want to cross. When you cross, the phase becomes indeterminate. Your integral error, numerical error will go to infinity. So, so you don't want to cross these things. So you want to cross in the origin and take a specific path. This is a branch cut and so forth. So you choose paths such that your numerical integration, even though your goal is to work and integrate from minus infinity to infinity, you work through in the complex plane. I can give you a color picture that explains. So the dark shades tell you the magnitude. That means the magnitude is close to zero. The more brighter spots tell you that the magnitude is larger, and the color tells you the phase. So from blue to red means there's a sudden jump of phase. So basically, you are coming through the red, the origin. You want to capture the high magnitude regions because you won't integrate zeros. No, numerically it doesn't make sense. So anyway, so that is one kind of work we've done in the past. The other one is a similar idea. You change f to g. G is an approximation of f, but easy to evaluate. And f minus g is small and oscillating signs. So that means when you integrate the errors, oscillating signs, the errors cancel out. So you replace f with an easy function to integrate, which may be G, and make sure that the errors are oscillating and reasonably small. It's a simple idea. So we have done that kind of work, and that might be used, for example, uh, real-time applications where they cannot do this heavy integrations, inverse problems. You have to shoot your weather radar, and estimate the size of the droplets. Rain is a changing thing. You shoot in different directions. Your radar, you immediately estimate how much rain is coming. So it's an inverse scattering problem that we are aiming at. Okay. So, and slowly changing tack to the physics side of things. This is one example. This again a data example was years before, but this is just for motivation. This might have impacted for many people in this room as well. So the issue here is everybody wants to use sunscreen. The sun is really harsh, and one of the things you require sunscreen is the titanium or any other UV absorption material. So titanium is a very good absorber that is typically used, and and one of the ideas is this is a electron micrograph, so it's just a very small dimension, 18 nanometers here. So you take instead of using titanium balls, you could use silica, which is harmless from a cost and a health perspective. Silica spheres and then nucleate titanium on them, just like the red titanium on the blue silica here. And then how much does this particle absorb compared to the ball of titanium? Turns out this absorbs the same amount, but it's 40 times less volume, say, for a 200 nanometer particle. So you can reduce the titanium use by about 30 times, 20 times um, by designing this kind of particles, and you don't have to fully fill up. That's what's the message of our work in doing these experiments and these simulations. And coming to the last, leg of this presentation. So the other area is working with more on the physics side, pure physics side, is this spontaneous emission. And the motivation is that, let's say you have a molecule and you want it to absorb light and then emit light in a different sequence. That's what typically happens. Could be Raman scattering or any other absorption emission mechanism. It absorbs a certain energy, photons have a certain energy, and emits another photon of a different energy. And you would want this molecule to increase the chances of this molecule getting excited. One way that is done is put these molecules very close to a metal surface, rough metal surface with gaps or rough features on the surface, and that increases the near field irradiation around the surface, and the molecule has higher chance of more opportunities to absorb the photon, and then it will send out a different color, and then you can sense that this molecule is this. You can even, it turns out today, surface enhanced Raman scattering, ACRS is the surface enhanced Raman scattering. You can even find a single molecule today's institute. So that is, so the one question that's been there for many decades is, okay, you increase the chances of absorption of the photon by this molecule, but what happened to the emitter? Does the surface absorb that also or not? Because you get this extra light because it is a very absorbing surface, okay? That's why you got the very close to the surface, you get a lot of photons. Okay? So what happens? Does this absorb the emitted photon? That has been a mystery because the experiments say otherwise. Okay, that you are getting very good benefit of putting the surfaces. That means it is increasing the exerting radiation, but not absorbing the photon that's coming. So that is a mystery for some time. And actually, we got into it by because of some other again anomaly. Is again at least the physics students here, even the others I think can catch this. It's quite simple. So you have an atom, and it turns out its probability of the excited atom emitting. Okay, this is on the emission side. The photon is higher if you have some scattering feature close by. Okay, the atom is very far away. Of course, it's classical. The photon comes, gets scattered, goes away. But if you have the atom close by, less than wavelength distance, then what happens is the probability, of course, can have the photon going scattered and directly it's not observable and so forth. So you have some. So what happens is now you have to look at the probability. Now the photon, after coming out of the atom, has different states to live by. In other words, instead of a homogeneous space around it, it has a scatterer. That means it can come out, scatter in different directions. So there are many more states to live in outside. So the higher chance of the atom emitting instead of turning it into other radiation, heat, blast, it is higher likelihood of throwing out the photon. So you can increase light emission and so forth by putting close proximity some strong scatterers. Okay? This is something that has been done in materials for 2 decades now. But one of the issues is this is scattering. But what if you put a particle which is not scattering? It is almost absorbing, mostly almost zero scatter. Okay? It turns out this also produces extra light, and that is not cannot explain it. Okay? It's not easy to explain from these kind of things. So that is another round we worked on. Of course, these two are related. That's what we learned later. Of course, not going into details, but it required a modification theory of how much is absorbed by the particles, how much is not absorbed. So the theory had to be modified because you don't seem to observe these small particles absorbing. Instead, they're enhancing the emission. So you have to explain this and this, and that's something we have done. So worked on for more than a decade. So summary, I just come to go back to the first slide. In fact, um, computation methods do assist solution of theoretical models, or mathematical models rather. I should have had mathematical models here. But the other aspect of computation and I'm going back to computation physics. Okay, so think from computation physicist point of view. In physics, now you are having computation and phenomenological models like more broadly can provide more theories. Like the previous example I gave you, I'm not going into the details how we solve and all those things, but it requires a combination of and phenomenology models, and it can give us new theory. So computation physics is okay, but if it's computation and physics, even better. That's what I'm saying. So I have to thank some of my recent students. Hari Prasad who worked on matrix analysis. Of course, he is right now in India doing algorithms for communication networks. All this uh, the emission, spontaneous emission problems worked on the Kritika. She is in Japan. Of course, Arunai with the high dimension integration. Applying similar, not the same method, but something else for ID biological data. Of course, I don't know what it's for. It's secret. So Abhishek worked the Intech research student to work error estimators. In fact, Puneet Jain and Krishna Maglani, I think, when they started this work. They did the estimators and then Abhishek still with them, and then in Google, he is the person who found the approximations G for F, when you're integrating and then find. So that kind of work. Atira, she took Hari's work and actually she's done some lattice, periodic lattices are very common in physics. So the matrix problem, Hari's eigenvalue problem, she has taken them and applied it to create solvers for those kind of people, physical sciences, and then she's going to work in physics. So that is all I have. But something I would, leave you with in the end is, of course, I know this is a time of internet and then ChatGPT now, so a lot of facts, information coming at you. But I think in the end, things remain the same. Mostly, of course, there is some change in how you do things. I think the goals and the rough principles remain same. That is, you are trying to build a lot of facts thrown at you. But science is like a house where each stone you use has to be unique. You're building a house with unique stones. It doesn't depend on number of stones you have. You have to build it up fully, and you have to know the relationship between the facts, hidden relationship, finding them. That's not simply a linear relationship of the number of facts you have. And that is, I think, still interesting. So I think we should all try to do that. That is all I have. So any questions are welcome.
So when we calculate errors, they're not always very easy to calculate first of all and even estimate sometimes. But how do we know how they eventually propagate through the system that we are working with? Because this may be like a small part of a big calculation, and then that big calculation may be like very important in some other application. So how do we work with that?
That's a very good and relevant question. So one of the things we do in numerical analysis of methods is we try to see how the error propagates through the method. Okay. And we have to do that because the moment we use a computer, we are rounding off stuff. So that means we are introducing errors every step of the way, right? So the errors should not propagate and blow up. That is a basic necessity for stability of any algorithm. So we do a stability analysis. You would have heard this word stability of any method. That comes from this. We precise that question that you asked, that the errors that you introduce should not add, multiply, and propagate and blow up. So that is something we have to do analysis carefully many times. And like I said, for numerical method, that's mostly done. But that is not very easy to do in every method. Most of the statistical methods you have bounds on, for example, the average error. You cannot say the worst case error what will happen. It's very hard to say. For numerical methods, that is mostly done. It's slightly challenging, but it's done. That is a numerical analysis of the methods, convergence, error, and so.
Also, has any work been done on using like machine learning to do the same? Uh, not calculations, but more like estimating the results.
I think it's being done. I'm not so sure, but I think I've heard that this kind of problem. I'm looking at it as a generic problem. Yes, or you have something being spit out, and you have to estimate something else. I think the same thing that we did, we could use machine learning, right? We are predicting errors from the residues. That's what we do. Huh? So you could use some machine learning kind of thing. Good, but I don't have serious thoughts on how it will work or anything. And it has to be very efficient. So that's one of the things. Every iteration, I don't know if I paused and talked about those methods I had in the slide. CG, GMRS, basically generalized minimal residual, conjugate gradient, those kind of algorithms. They're all order of n squared. So each iteration takes n squared. So you should not, increase the cost of the iteration too much. You can do an estimation, but it should be very cheap. So that is the goal. So yeah, if machine learning can be trained well, and what kind of errors, what kind of matrices, it will depend on all that. Certainly for special cases of matrices, I think it could be possible because you have a rough idea of the behavior of the residues for what kind of right hand sides, what in general also it is possible. I am talking about a specific problem. In general also, I think you can take residues and try to predict errors. That's in principle not a bad idea.
Thank you.
So could you talk more about the iterative methods? For example, how do you make the initial random guess, and how do you make sure that you do not converge on some value which is far away from your answer if you are constantly going towards that direction? How do you make sure you are at the right path?
Yeah, that's again a very relevant question. So it's related to what he asked, but slightly different. In the sense that you see, depends on the matrices. For example, symmetric positive definite matrices. You have typically full rank. You have a nice unique solution, and conjugate gradient for solving linear systems offers you that unique solution. Um, but there are other situations where you don't have a unique solution, you don't know which one you are converging to. Those issues do exist, especially rank deficient problems. You won't know, there is no unique solution, so you converge to one of them. So that is the kind of cost you pay in iterative methods. Um, and of course, you're solving a problem which cannot be inverted. There's no inverse. You're solving using iterative methods. So you have multiple solutions. You'll converge to one of them. So that issue is there. You cannot go around it that easily. But it can converge to one solution. That convergence guarantees are provided by those methods. Okay. And that is restricting to linear. I am restricting myself to linear solve. Broader sense, yeah, it is work in progress. I think if we, we have to think about these things.
So there's a question here from our online viewers. They're asking if you're using quantum-based modeling for your spontaneous emission problems.
Yeah, obviously. This we have to. I don't use the word quantum so often. I try to, but yes. So you can see that that's why classically the atom is far away. Then it's just a simple scattering and absorption problem. When it's very close, so what happens is you have the photon can be an excitation in the atom or an excitation of the particle, and what happens when it can absorb. So certainly yes.
Sir, regarding the residues, when you had mentioned that the matrix A might affect how like badly the residues might vary. Sir, how is that? Just can you explain?
So yeah, I will explain that. So this A matrix has something called a condition number. Some of you might have heard about condition, well conditioned, ill post. These are all different terms used for roughly the same things. So well conditioned meaning if you have AX, let's say, if you change X slightly, the B changes slightly. That is a well conditioned A. Okay. A badly conditioned A means, or a high condition number means, you multiply, make a small change in X, the B changes very much. Okay. So that is a badly conditioned A. So those kind of situations, those kind of matrices A is where you have this, because it's A into X minus XK is the residue. So A creates a lot of problems depending on the direction of X minus XK. For some directions A won't bother you. Some other directions A will make a small change in the vector will make a big change in the product vector B. So that is the badly conditioned matrices. So another relevant thing here is why is condition number of A, why should condition number of A increase? Uh, Typically when the applications you are trying to solve the problem more precisely by finer discretizations or more involved models, that's what's happening as we progress. Your condition number of A increases because you're making a very fine model of the system. And if you are not careful, or even otherwise, there's a chance that the condition number can go up. So these estimators become more important. The 20 years back, 30 years back, you could stop by residue for most problems. Now, as condition number of A is increasing and the size of the problem is also increasing, remember or imagine you're running the supercomputer for 2 days, the amount of energy, water required. If you could stop in one day, even though it reduces computing by half, you could say in some terms, half is not a big reduction. It depends on how you think about it. But in terms of resources, if you're running a big system, it reduces. So stopping, like you said, that's why. So I think as we progress, some of the things which are not important 20 years back is becoming more. If you wouldn't worry about that for 20 years.
Okay, it's related, but how is our approach to chaotic systems? How does this proceed?
So I don't work in that area, so I don't think I can say anything very useful here. Um, so I mean, if I have to, I'm trying to understand you like something like weather systems. Is that what you
Chaotic systems where
it's related to wheel condition? No, that's why I'm guessing. So you're saying a small change in input makes a big change in the weather system. Okay. So how do you address those kind of issues you are saying? Uh, like I said, you have to maybe make your model, put more thought into the model, because there are two reasons the your model could be badly conditioned. One, inherently it could be a highly chaotic system. One, your model could be ignoring something, important. No, the parameter. That's why I said have a real world problem. You have to choose your parameters properly. Hopefully, they're all independent, so the problem size remains small. Still, you capture everything. So those kind of things are there. So I think right in those stages itself, I think we have some problem. That's my outsider's guess. Okay, so there could be real chaotic behavior inside, or we could be having not so well posed, mathematical models. So both could be resulting in this chaotic situation. And you are saying, how do you address? No? So one thing we do is numerically when we solve this kind of problems, we use something called precondition. What we do is we first multiply a and remove certain directions which are troublesome. That is where a becomes slightly smaller, it increases the error. Okay, so we kind of compress those dimensions and then solve a execute b. So that makes sure, like you said, the errors don't propagate, blow up, or things like that. That is one practical way of solving the problem. But that will again come back to you saying whether that solution is what the right solution. It will be slightly perturbed from the actual solution because you have done preconditioning. And again, so it's a small cost to pay. That's something we do practice. There will be precondition. Well, the problem is not so well posed. We do preconditioning, and there's something called regularization, which I won't talk about. But these two things are done.
Sir, you had mentioned discretization a few times. So, what is actually discretization?
So basically, so let's say you have a continuous this wall. There are two ways of discretization of this to represent the wall. One is lumped. You can put points in the wall that represent the mass of the wall. So all the properties of the wall are now imposed on the points, okay, that represent the wall. And between the points, there is nothing. There is empty space. That's a lumped representation of the wall. So that you have these nodes where all the mass, stiffness, everything is there, and the 2 points have some interaction which will be based on the stiffness. That's one lump discretized representation of the wall. Okay. You could discretize and also represent the wall in a distributed, the mass and the stiffness is distributed like finite elements or something. But actually, no, uh, that is still not continuous. No, that's why we call discretized. So it has finite number of elements. Finite. So you discretize into, let's say, 10 raised to 5 elements, and that is discretization. Because wall is continuous. At least still atoms are there. Let's forget about atoms and stuff. Let's assume it is continuous. Now you have reduced it to 10 raised to 5 or whatever number of finite elements. So that is called discretization.
So while we are on the topic of discretization, I would like to ask, like many problems in physics have gauge invariants and some kind of invariance in them. And when we change, say, the reference frame, we go into some contraction or expansion along the axis or something like that. How do we handle that in discretization? For example, if I have, say, space-time in 2 dimensions and there is a Lorentz contraction. So the homogeneity of space-time is lost. How do we handle that in numerical methods or anything like that?
So I can't address the application, specific application you're talking about this. I don't work on that, but I can give you a rough high level picture on that because similar issues happen. For example, even if you model flows, you know, turbulence and stuff, there are certain areas where you have to, the mesh has to be very different. So if you look at a real world meshing discretization that is done today on a computer, the mesh is not like some square nice grid. Okay? The mesh will be really complex. Meshing itself is a complex operation that's um, done before this operation. So the mesh will be distorted, and there are meshing elements that make sure that depending on the boundary and problem that you are solving, you have to come up with meshing elements that match the boundary. So people do have different ways of meshing. They don't have the mapping or change of space and contraction. They don't have that, but it is a similar thing that the computation is more reconditioned in those corners of the simulation where the boundary is changing, and some other place the answers are not so reconditioned. So it's like a combination of multiple smaller problems that you're solving. Some are bad, some are good. So based on that, your meshing is adaptable. So adaptive meshing is itself a whole area. So I think those kind of things will apply when you do transformations and stuff. The mesh itself can be transformed. So that also happens. So you have, for example, there are methods where you actually mesh some domain. The domain is transformed, the mesh also transforms. So you have to be working on it.
Because in those areas, solutions can remain the same even though we have varied the reference frame. So you are saying that if we are dealing with some problem, we are not dealing with the right reference frame to solve it, a computer can probably find us the right reference frame, which can simplify the amount of numerical analysis we should do.
Yeah, I think it is
That
possible.
can be possible.
Yeah, that is roughly what is done in some problems like flows and those kind of things. So I don't know how to translate that to the problem, but roughly those kind of things are being done.
Sir, in your talk, you had said that there was 4%, 5% error in the actual value. But if we don't know what the actual value is, then how do we calculate that 4% or 5% number?
So relative error, I see. What's the relative? So yeah, so x minus x dash is the guess divided by x. I'm saying relative terms. Yes, 4%, 5%. You look at bounds. Okay, so one, like I said, numerical analysis, you would have closed form. If you are able to do that kind of an analysis in certain methods, numerical methods, it's mostly possible. So you will see how the thing converges to the actual thing, and you will be able to say, given so many iterations, the error is upper bound by certain number. But in certain things, it will be heuristic. You cannot tell for sure. That's why in statistical methods, for example, you cannot guarantee that if you do so many samples, you will get guaranteed less than this error. Nobody can say that. They can only say that the average error is less than certain thing, which means if you do the same statistical simulation many times, the average error will be less. Okay, that is all. Say. And in those cases, also many times they report using heuristic. They do tests on certain functions, certain domains, and then tell you. And the bounds are usually on the average. So yeah, for sure you cannot tell on certain methods, but certain methods, like I told you, for numerical methods, linear solve, you can give exactly the bounds, the upper bound of what worst case values. The statistical method, the errors, I guess 4%, 5%, to me looks very good error. And that's good to achieve. If you achieve that, I mean, I'll be happy. Okay, all right. Yeah, nice talking to you all.
Thank you,
See
sir.
you around in camp.